Okay, so we are going to look at the practice problem that was posted titled Speed and Velocity number 1. So you and your roommate are heading to Ted's Pizza from your house, which is 400 meters away. It's really close. Quarter of the way there, you realize you've forgotten your wallet. Your roommate waits for you to run back and get it, and the two of you walk to Ted's together. You arrive at Ted's 15 minutes after you first left together. Part A, which one of you had the greater velocity? So we really need to think about what velocity is all about. We want to remember, and this is a conceptual problem, so we're not going to calculate it, we're just conceptualizing it. Thinking about what velocity is the displacement, and we're dealing with average velocity, yet still, it's our displacement over the time of the motion. Now thinking about displacement, that's our initial position relative to our final position. Well, you both ended up at Ted's, your final positions were the same, you both started at your room, your initial positions are the same, so your displacement was the same. You ended and started at the same location. Now, you went a quarter way, ran back, but your roommate hung out there. So you started at the same point in time and you ended at the same point in time. So over the course of whether or not you were running back and forth and he was just, or she was just hanging out there, your total time was the same. So your displacement was the same and your total time was the same. So at the very least, the magnitude of our velocity is the same. Same displacement, same time. But what about the direction? Because we have to compare both. Well, you were both going from your house to Ted's, and whether you identify that direction as positive or negative, it's the same for both. So in this case, both initial and final positions were the same. Both times were the same. So velocities are the same. All right. So let's see if that actually works. Let's look at the different velocities. So part B says, what was your velocity in meters per minute? And what was your friend's velocity in meters per minute? And I'm using the meters and the minutes so we don't have to do any conversion in this particular kind of just basic velocity speed example. So for you, well, if we're going to determine the average velocity, we need our final position minus our initial position over the time of the motion. So our final position was at Ted's. Oh, we need to know what the world looks like. We have to identify where the positions are. So let's do that. So if this is our situation, it tells us that Ted's house is 400 meters away. Well, it doesn't say whether it's east or west. Problem doesn't specify that, so we get to pick it. So let's say our house is here, and Ted's is here. Now, you'll notice in the solution I've actually drawn the world a little bit differently. So I want you to be able to differentiate between those two as an extra way of fully conceptualizing this problem. All right, so here is your house, and here is Ted's. So let's identify an origin. Let's say Ted's is the origin. Again, this is different in the printed solution, so now you have two different ways to solve the same problem, helping you understand that it should all match with our coordinate system and our positions that we've identified. So some extra practice. So here is our position of the origin. If that's the origin, then my house, which is 400 meters away, is at a positive 400 meters. As I have drawn it, my house is at a positive 400 meters. It's to the right of Ted's, east of Ted's, north of Ted's, whatever you want to think about in terms of that coordinate system. So now let's use that information to solve our problem. Well, our final position was Ted's in our walk there, whether I went back and forth to my house or not, and Ted's is at 0. So I end at 0 meters. My initial position was my house. My house is at a positive 400 meters. And the time that I am traveling through that motion is 15 minutes. That's given in the problem. So if I use this information to solve for my average velocity, final position is 0 minus initial position of 400 all over 15 minutes, then I find that my average velocity is a negative 26.7 meters per minute. What does that negative tell me? Well, it tells me I'm moving to the left on average. And if I started at my house and I ended up at Ted's, on average I ended up to the left. I moved to the left. So that's consistent with what I would expect. All right, well, we thought that our friend had the same velocity, so let's check it out. So if we look at our friend, well, the average velocity, again, is the change in position, our displacement over time. So where does our friend end up? Well, he ends up at Ted's Pizza. And where does he start? Well, he starts at our house, which is, again, at 400 meters. So using then the time he travels, even though he sat and hung out for a little bit, he still got there in 15 minutes. So 0 minus 400 over 15 gives me negative 26.7 meters per minute. And indeed, we have the same average velocity. Well, what about speed? Do we have the same speed? Well, let's remind ourselves, so this is part C. Let's remind ourselves about what speed is. The average speed, remember, is our distance over the time that we travel. So the total lengths. Now, if we think about you, what was your path? This is path dependent. You went from your house, you got a quarter of the way there, had to go back to your house, and then go off to Ted's. Your buddy, well, he went, got a quarter of the way there, hung out, waited for you, and then went off to Ted's. His total lengths are less. So you have a greater distance than your friend because you traveled more lengths. If you have a greater distance than your friend, it took you the same amount of time. This tells us that your speed has to be greater than your roommate's speed. So let's see if that pans out. All right, part D. What is your speed? Well, your speed is going to be the total lengths over the time. So what does that look like? Well, we start at position 400. We travel a quarter of the distance. So that's 100. So 100. And we go back. It's another 100. So we have 100. We go back to our house for 100. We come back to the waiting spot for 100. And then we go on to Ted's. So 100 plus 200. Back to the waiting spot, on to Ted's. So we get a total of 700, 100, 100, 100, 100. We get a total of 600. I looked at my notes and I looked at my pages and that's something I was imagining because it's 600 meters. Our total distance is 600 meters. We do that in a time of 15 minutes. And we see our distance to be 40 meters. I'm sorry, our speed to be 40 meters per minute. So that's you. You. What about your friend? Well, what did they travel? The total length in time. They traveled the 100 meters. Then they hung out and waited for you. And then they went on with you in that next length of 300. They did that all in 15 minutes. So we have 400 meters in 15 minutes. And that gives us 26.7 meters per minute, which is less, just like we said. All right, so what about direction? We don't care about direction because it's distance. We just keep adding up those lengths. Direction is not important in that situation. And we see that the more lengths we do, us back and forth because we forgot our wallet, is larger in the same amount of time. So we have a higher speed. All right, good job.